having looked at the different chemical engineering applications of differential energy balance, now let us start deriving the differential energy balance. So, as usual we will start with the control volume in our familiar experimental setups. The left hand side shows the flow through the pipe, and the right hand side setup shows flow through the tank, and in the left hand side you have one inlet, one outlet, and in the case of the tank you have two inlets and then one outlet. Okay. Now, what is the control volume which you should imagine over which you are deriving the differential energy balance? In the case of the pipe and in the case of the tank, we take a small control volume inside the domain, and that is what is shown by the yellow color region in both the experimental setups. And so, these are our control volumes, they are inside the domain, it could be in the pipe, it could be in the tank. And for this control volume, we are going to take into account the rate of change of energy, energy flowing in, flowing out, and then heat added to the control volume, then work done on the control volume. So, in a sense we are going to apply the integral energy balance for this small control volume. Okay. So, let us start with the integral form of energy balance equation. This is what we have been doing while deriving all the differential balance equations. We start with the integral form of the corresponding balance equation. So, in this case we are starting with the integral energy balance equation. So, let us write down the integral energy balance equation. The first term tells about the time rate of change of total energy. Next term tells about the net rate at which energy leaves through the control surface, and the terms on the right hand side tell about net rate of heat addition, net rate of work done. Now, for a fixed control volume, as we have done earlier, we will bring the time derivative inside the integral sign, and now it should be written as a partial derivative. The reason is that when the derivative was outside, we integrated over the control volume. So, all the spatial variations have been taken into account, and then only time remained as the only independent variable. So, we wrote it as d by dt, but now it is inside the integral sign. Rho and E can vary with space. So, now both spatial variation and time variation are there, and so we represent as partial derivative, and the remaining terms are same. Now, we are going to apply this integral energy balance equation for this control volume, and how should we imagine? As we have done earlier and as seen in the experimental setups, we should imagine this control volume inside a pipe and inside a domain, and because of our restriction to Cartesian coordinates, we should imagine a pipe of rectangular cross section. Also like to mention that this small control volume could be in a solid as well. We are talking about energy balance, so it could be, let us say, conduction in a solid. So, this small control volume could be inside a pipe where there is a flow taking place, or it could be a solid. So, to show an example, for example, this is a control volume and this could be in a inside a pipe, okay. Or you can imagine this as a domain, then control volume is something inside this, or it could be a solid object like this and your control volume is inside the solid object. So, two ways of imagining, because you are going to apply this differential energy balance for two examples, one for a solid and one in a fluid domain. So, our objective in the next few slides is to apply this integral energy balance equation for this small control volume. So, let us proceed. That is the integral energy balance equation which we have seen in the previous slide, written for a fixed control volume. Now, let us take term by term and apply for this small control volume. Let us take the transient term. As we have done earlier, we will take an average value of rho and E within this small control volume. The control volume has dimensions of delta x, delta y, delta z, and because we are taking an average value, it is a constant inside the control volume. So, dou by dou t of rho E can be taken outside the integral sign, and then we are left with integral dV over the control volume, and the volume of this control volume is delta x, delta y, delta z. And like to mention and specify that E here represents the total energy per unit mass, which includes the internal energy per unit mass, the kinetic energy per unit mass, and the potential energy per unit mass. And then, like all the other differential balance equations, we will finally divide by delta x, delta y, delta z and shrink it to a point. So, what we will do is divide now itself and keep the terms ready, so that finally we can substitute in the integral energy balance equation and then take the limit finally. So, we will keep these terms ready after dividing by delta x, delta y, delta z. That is what we will do for all the terms. Now, let us proceed with the convection terms. Let us look at the significance once again. It represents net rate of flow of total energy out through the control surface by convection. So, it tells about the rate of flow of energy, and it represents the net rate of flow of total energy out through the control surface by convection. Now, many terms are very familiar to us. We have looked at this several times in while deriving other conservation equations. Only difference is that now we are applying for total energy. What this tells is about the flow of energy, and now let us look at the control volume. The arrows represent the flow of energy entering and leaving through the respective phases. So, we have 6 phases. Energy enters through the left phase, the bottom phase and the rear phase, and it leaves through the right phase, the top phase and the front phase. And now, what we should do is express this integral expression for the 6 phases. Let us do that. This term has been represented here. We have rho here and that is written here. We have E here and that is written here, and then we have V dot n. The velocity is perpendicular to the phase, and so V dot n is written as V here, and then as we have done for rho and E to have an average value within the control volume, in this case we will take rho, E and velocity to have an average value over this phase, and since it is an average value over that phase, it is a constant across that area, and then we can take out all the terms, that is rho, E, V outside the integral, will be left out with integral of dA, and that is written as A here, and this has to be written for 6 phases, 3 outlet phase and 3 inlet phase, and for the outflow phase V dot n is positive and that is why it is positive here, and for the inflow phases V dot n is negative and that has been taken care by us explicitly. Okay. So, the integral rho E V dot n dA has been expressed for the 6 phases in this expression, 3 outlet phases, 3 inlet phases. So, just to quickly summarize, rho appears as such, E appears as such, and V, the velocity is perpendicular to the area. So, written as V here, and rho E V are taken as average and as a constant. So, integral dA gives A, and I of course represents the particular phase, outflow phase or inflow phase, and positive for outflow phase and negative for inflow phase. Now, what we will do is consider the phases pairwise and apply this expression. Here we have considered the 3 outflow phases and 3 inflow phases. So, we will take one outflow phase, one inflow phase, let us say the x direction, and then see how to express that. Now, let us look at the 2 phases along the x direction, the inflow phase and the outflow phase, that is the left phase and the right phase. Now, what is the rate of flow of total energy entering the left phase? Okay. That is what is shown here. Now, how do we interpret this? As we have been doing earlier, we can interpret in 2 ways. First, the easier one, Vx is the velocity, we multiply by area, we get the volumetric flow rate, multiply by density, we get the mass flow rate, and then we multiply by the total energy per unit mass, then we get the rate of flow of total energy. Okay. So, velocity then multiply by area gives volumetric flow rate, by density gives mass flow rate. So, then we will have mass flow rate, and that if you multiply with the total energy per unit mass, then we get rate of flow of total energy. What is the other way of interpreting? Vx is the volumetric flux, and then if you multiply by rho, you get the mass flux, multiply by area, we once again get mass flow rate, multiply by the total energy per unit mass, we get the rate of flow of total energy. So, 2 ways of interpreting. Now, rho, Vx, E all can vary spatially, and the left phase is at x, the right phase is at x plus delta x. So, we have indicated that the whole term is evaluated at x, the whole term is evaluated at x plus delta x. So, these terms put together represent rate of flow of total energy entering at x, and that is what is written here, and these terms represent the rate of flow of total energy leaving the control volume at x plus delta x, and those are written here. So, what we have discussed now is how to express the rate of flow of total energy entering and then leaving through the phases in the x direction. Okay. So, now let us extend this for all the other 3 directions. What we have seen in the previous slide are these terms. Now, what does this represent? This represents rate of flow of energy leaving, and this represents rate of flow of energy entering. When I say energy, I mean total energy. So, this two terms put together represents net rate of flow of total energy leaving the control volume through the control surfaces in the x direction. So, let us write similarly for other directions. There is energy entering at the bottom face and then energy leaving at the top face, and those two terms are shown here. Once again we should take as rate of flow of energy leaving minus rate of flow of energy entering, because this integral terms tells about net rate at which energy leaves the control surface. Similarly, in the z direction, and those are shown here, what is leaving and what is entering. So, as we have discussed earlier, let us divide by delta x, delta y, delta z and keep it ready. So that later on we can take limit delta x, delta y, delta z tending to 0, so that becomes a point. Okay. So now we should note that they once again represent rate of flow of total energy, the net rate of flow of total energy leaving, but now because we are divided by delta x, delta y, delta z, it is per unit volume, and now it accounts for all the three directions. So here it is in terms of only rate of flow of energy and then net rate of flow of energy leaving, that is for x direction, and then for y direction, then for z direction. When we divide, we get here as per unit volume basis, also accounting for all the three directions. Now, like to compare this control volume with the control volume which we have discussed earlier while deriving the differential mass balance and differential momentum balance, and those control volumes are shown here. So this slide shows the three control volumes, one which we use while deriving the differential mass balance, the second one, the middle one, shows the control volume which are used while deriving the momentum balance, the third one which I have seen just now. Okay. So let us understand them. Let us take this term. What does that represent? It represents the rate of flow of mass entering in the x direction, okay, and we interpreted that as the velocity into area, the volumetric flow rate multiplied by mass gives the mass flow rate. Okay. Then when we discuss the momentum balance, what did we do? We took the same term, but now included a Vx here, so that now it represents the rate of flow of x momentum entering the x direction. Why is it? Without Vx it represented the rate of flow of mass, we multiplied by Vx which is the momentum per unit mass, and then we got rate of flow of momentum entering in the x direction. Now what is that we have done? Once again taken the same term rho Vx delta y delta z and then included a total energy per unit mass, and now it represents rate of flow of total energy entering in the x direction. So it should be easy if we compare all the control volumes, all the terms of similar physical significance, they represent the particular property, they represent the corresponding property brought in and brought out in all the three directions because of convection. So if we understand that, then from one control volume we should be able to draw the other two control volumes, and in fact that is how these figures have been prepared. The first figure was prepared, then copied, pasted, added the Vx, replaced the Vx with E and got the third figure. Okay. So that also it may look like copying and pasting and replacing, but that has a physical significance behind it, meaning that all the 3 control volumes represent with these terms represent the flow of that particular property entering and leaving, and all these terms represent the convection term. Okay, now let us go back to our integral form of energy balance equation. Let us see what is that we have done and where should we proceed further. Now, we have applied this integral energy balance equation for the small control volume. We have expressed the left hand side for the small control volume, both the transient term and the convection term. Now, we will focus our attention on the right hand side, and in the right hand side we will focus our term on the net rate of heat input or heat addition. Okay. So, what is that we are going to discuss now? How do we express that Q dot net in, which represents net rate of heat input for the small control volume. Okay. Now, we know that there are 3 modes of heat transfer: conduction, convection and radiation. Let us discuss what do we include here and what do we exclude here. Okay. In fact, first we discuss the exclusion, so that we can include whatever is required. Okay. First, radiation. Radiation is significant only at high temperatures, so we neglect. In fact, not even high temperature, it is at very high temperature. Okay. Let us say 1000 Kelvin, 1000 degrees centigrade, order of such a high temperature radiation is important. We will restrict to not so high temperature. So, let us neglect radiation. Now, convection, which represents heat transfer occurring at a fluid solid surface, is also not included. The reason is that, remember when we discussed our small control volume, let us imagine this is our fluid domain and our control volume is inside. So, when you are considering a control volume inside, that is not at the boundary between let us say a solid and a fluid, our region is inside. So, because we are considering a control volume inside the fluid domain, we are not including the heat transfer by convection, which happens at fluid solid surface. It does not mean we are ignoring that. Remember, we had differential equations, we discussed about boundary conditions. So, when we solve the energy balance equation, these convection terms appear as boundary conditions. We may not discuss, we may not come across an example in this course with such a boundary condition, but in your heat transfer course you will come across a case where the differential energy balance equation is solved using the convective heat transfer as a boundary condition. So, radiation is not included because we are not considering very high temperature. Convection, which represents heat transfer at fluid solid surface, is not included in the differential energy balance equation. In the conservation equation, it is not included because that occurs only at solid fluid interface, our control volume is somewhere inside. Okay. So, what is left out is heat transfer by conduction, and let us include the heat transfer by conduction through all the 6 phases of the control volume. Okay. So, now our objective is to represent this rate of heat input through the control surfaces by conduction only, and that is what is shown in this control volume through this different terms here. Here Qx represents the heat flux in the x direction. Qx represents the heat flux in the x direction due to conduction. And how do you represent heat flux? We represent that as rate of flow of heat per unit area, and when you multiply by the area, we get the rate of flow of heat, and this heat flux can vary with spatial location, and so we express that as q x evaluated at x and similarly q x evaluated at x plus delta x, and this represents rate of heat input by conduction, and this term represents rate of heat output by conduction. Similarly, we have heat input in y direction, heat output in y direction, similarly in the z direction as well, heat input and heat output. So, let us write down all of them. So, our focus is on the net rate of heat input or heat addition, rate of heat input by conduction at x. So, we are representing this term is q x at x into delta y delta z. Once again want to specify that q x represents heat flux in the x direction due to conduction, and flux is always any quantity per time per area. So, we have rate of flow of heat which has per time in it per unit area multiplied by the area which is delta y delta z, we get the rate of flow of heat, and because it is inflow we are writing it as rate of heat input by conduction, and at the right phase we have rate of heat output by conduction, and what is the net rate of heat input by conduction next direction. Want to stress here that the right hand side what we have is net rate of heat input. So, now we should take q x at x and then subtract q x at x plus delta x. Why is that? This represents heat input, second term represents heat output. What we want is net rate of heat input, that is why we subtract output from input. So, we have input minus output representing net input. This in contrast to the convection term which was outflow minus inflow. Okay. So, this has to be kept in mind. When we did the convection term it was net outflow. So, we always throughout all the conservation equations we have been considering it as outflow minus inflow, so that it represents net outflow. But now on the right hand side we have net rate of heat input. So, we should take the term as input minus output or heat input minus heat output. So, that thus that term represents net rate of heat input. Okay. This convention has to be kept in mind, so that we take care of the sign correctly. Okay. So, let us do it for the other directions. So, net rate of heat input by conduction in the x, y, z directions. We have to just repeat it for other directions with the corresponding area. So, for example, q y into delta z delta x entering at y, leaving at y plus delta y. For all the directions it is heat input minus heat output. Okay. So, as for the other terms on the left hand side, here also we will divide by delta x delta y delta z and keep it ready with us. So, here the significance is net rate of heat input by conduction and includes all the three directions. When you divide by delta x delta y delta z, now these terms represent net rate of heat input per unit volume, taking into account x direction, y direction and z direction. So, here the significance is net rate of heat input per unit volume.